To calculate the general lighting and general use receptacle load for a commercial building, you'll need to consult the National Electrical Code, specifically Table 220.3 and Table 220.13. These tables provide the necessary information to determine the load requirements and apply the appropriate diversity factors. Let's consider a scenario where you need to calculate the general lighting and general use receptacle load for a 30,000 square foot bank. The formula you'll use is load equals area times load per unit area times diversity factor. Now let's break down each component. Firstly, the area. In our example, the area is given as 30,000 square feet. Secondly, the load per unit area. According to Table 220.3 of the NEC, banks typically have a load of 3.5 volt amps per square foot for general lighting and general use receptacles. Thirdly, the diversity factor. The diversity factor is a crucial element in load calculations, accounting for the fact that not all electrical loads will be operating at their maximum capacity simultaneously. For lighting loads in commercial buildings, Table 220.13 of the NEC allows the use of a demand factor. In this case, it references a demand factor of 1.25 for general lighting in banks, representing that not all lights will be on at the same time. This assumes that only 80% of the lighting will be in use at any one moment. Now let's plug in the values into our formula. Load equals 30,000 square feet times 3.5 volt amps per square foot times 1.25. Multiplying these values, 30,000 times 3.5 times 1.25 gives us a total of 131,250 volt amps. Now let's convert this volt ampere value to kilovolt amps or kVA. To do this, we divide the volt ampere value by 1000. Thus, 131,250 volt amps divided by 1000 equals 131.25 kVA. Therefore, the general lighting and general use receptacle load for a 30,000 square foot bank is 131.25 kVA. The NEC provides guidelines for calculating electrical loads in various types of buildings. It is important to consult the latest edition of the NEC and follow the specific requirements for the type of building you are working on. These calculations are essential for sizing electrical panels, conductors, and other electrical equipment to ensure a safe and reliable electrical system. Now let's go through another example to reinforce these principles. Suppose we need to determine the general lighting and general use receptacle load for an office building with an area of 50,000 square feet. Firstly, identify the load per unit area. Referring to NEC Table 220.3. A. We find that office buildings are typically assigned a load of 3.5 volt amps per square foot. Secondly, determine the applicable diversity factor. In this case, we again refer to Table 220.13 of the NEC, where we find that a demand factor of 1.25 can be applied to general lighting loads in office buildings. Thirdly, apply the formula. Load equals area times load per unit area times diversity factor. Plugging in the values, we get load equals 50,000 square feet times 3.5 volt amps per square foot times 1.25. Performing the calculation, 50,000 times 3.5 times 1.25 equals 218,750 volt amps. Finally, convert to kVA. To convert volt amps to kVA, we divide by 1000. So, 218,750 volt amps divided by 1000 equals 218.75 kVA. Therefore, the general lighting and general use receptacle load for a 50,000 square foot office building is 218.75 kVA. Keep in mind that these are general calculations and specific installations may have additional requirements or considerations. Always consult the NEC and local electrical codes for the most accurate and up-to-date information. It's also important to consider any additional loads that may be present in the building, such as HVAC systems, elevators, or specialized equipment. These loads should be calculated separately and added to the general lighting and receptacle load to determine the total building load. Additionally, consider the impact of energy-efficient lighting technologies such as LED fixtures, which can significantly reduce the lighting load compared to traditional incandescent or fluorescent fixtures. When using LED lighting, be sure to use the actual wattage of the fixtures in your calculations, rather than relying on the volt-ampere rating. Furthermore, it's essential to understand the concept of continuous loads. A continuous load is defined as a load that is expected to operate for 3 hours or more at a time. For continuous loads, the NEC requires that the branch circuit be rated for 125% of the continuous load. This means that if you have a continuous lighting load of 10 amps, the branch circuit must be rated for at least 12.5 amps. In addition to the general lighting and receptacle loads, you may also need to calculate the load for specific appliances or equipment. For example, if the bank has a large computer server room, you'll need to calculate the load for the servers, cooling equipment, and other related equipment. The NEC provides specific guidelines for calculating the load for various types of equipment. Also, remember to consider the voltage drop in the electrical system. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source due to the resistance of the conductors. The NEC specifies maximum allowable voltage drop for both branch circuits and feeders. It's important to calculate the voltage drop to ensure that the equipment operates properly and to prevent overheating of conductors. The length of the circuit, the size of the conductors, and the amount of current flowing through the circuit all affect the voltage drop. In summary, calculating the general lighting and receptacle load for a commercial building requires a thorough understanding of the NEC, as well as careful consideration of the specific loads and requirements of the building. By following the guidelines outlined in the NEC and paying attention to details such as diversity factors, continuous loads, and voltage drop, you can ensure that the electrical system is safe, reliable, and efficient. These calculations form the foundation of electrical design and are crucial for ensuring the proper functioning of any electrical installation. Let's delve deeper into the concept of demand factors and how they apply to different types of occupancies. The NEC provides demand factors for various types of loads, including lighting, receptacles, and appliances. These demand factors are based on statistical data and engineering judgment, and they represent the percentage of the total connected load that is expected to be in use at any given time. For example, Table 220.42 of the NEC provides demand factors for dwelling units. These demand factors vary depending on the number of appliances and the total connected load. Similarly, Table 220.44 provides demand factors for non-dwelling unit receptacles. These demand factors are based on the assumption that not all receptacles will be in use simultaneously. When applying demand factors, it's important to understand the specific requirements of the NEC and to consider the specific characteristics of the installation. For example, if you are designing an electrical system for a hospital, you may need to use different demand factors than you would use for an office building. The NEC also provides guidelines for calculating the load for electric vehicle charging equipment. As electric vehicles become more popular, it's increasingly important to consider the load requirements of EV chargers when designing electrical systems. The NEC specifies the minimum size conductors and overcurrent protection for EV chargers, as well as the requirements for ground fault protection. Furthermore, it is also necessary to consider the impact of harmonics on the electrical system. Harmonics are currents or voltages with frequencies that are multiples of the fundamental frequency, which is typically 60 Hz in the United States. Harmonics can be caused by nonlinear loads such as electronic ballasts, variable frequency drives, and other electronic equipment. Harmonics can cause a variety of problems, including overheating of transformers and conductors, malfunctioning of sensitive electronic equipment, and increased energy consumption. The NEC provides guidelines for mitigating the effects of harmonics, including the use of harmonic filters and other mitigation techniques. Remember to always consult with a qualified electrical engineer or electrician when designing or installing electrical systems. Electrical work can be dangerous, and it's important to ensure that all work is performed in accordance with the NEC and local electrical codes. A qualified professional can help you to properly size conductors, select overcurrent protection devices, and ensure that the electrical system is safe and reliable. Furthermore, always keep accurate records of all electrical calculations and installations. These records can be helpful for future maintenance and troubleshooting, as well as for ensuring compliance with NEC and local electrical codes. The electrical system is a critical component of any building, and it's important to take the time to design and install it properly. By following the guidelines outlined in the NEC and consulting with qualified professionals, you can ensure that the electrical system is safe, reliable, and efficient. Now, let's discuss the importance of proper grounding and bonding in electrical systems. Grounding and bonding are essential for protecting people and equipment from electrical shock and fire hazards. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and energize the circuit. Bonding connects all metal parts of the electrical system together, creating a low impedance path for fault current to flow. The NEC provides specific requirements for grounding and bonding, including the size and type of grounding conductors, the location of grounding electrodes, and the methods for bonding metal parts. It's important to follow these requirements carefully to ensure that the electrical system is properly grounded and bonded. Improper grounding and bonding can create a dangerous situation, increasing the risk of electrical shock and fire. In addition to grounding and bonding, it's also important to consider the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect people from electrical shock by detecting small amounts of current leakage to ground. When a GFCI detects a ground fault, it quickly trips the circuit, preventing a dangerous electrical shock. The NEC requires GFCIs in many locations, including bathrooms, kitchens, and outdoor areas. It's important to install GFCIs in accordance with the NEC to protect people from electrical shock hazards. Now let's consider the different types of wiring methods that are permitted by the NEC. The NEC specifies the types of wiring methods that are permitted for various applications, including residential, commercial, and industrial buildings. Some common wiring methods include non-metallic sheath cable, or Romex, electrical metallic tubing, or rigid metal conduit, or RMC, and flexible metal conduit, or FMC. Each wiring method has its own advantages and disadvantages, and the choice of wiring method will depend on the specific application. The NEC provides guidelines for installing each type of wiring method, including the spacing of supports, the methods for making connections, and the requirements for protecting the wiring from physical damage. It's important to follow these guidelines carefully to ensure that the wiring is installed safely and correctly. In addition to the wiring methods themselves, it's also important to consider the types of conductors that are used. The NEC specifies the types of conductors that are permitted for various applications, including copper conductors and aluminum conductors. Copper conductors are generally more expensive than aluminum conductors, but they have a lower resistance and are more resistant to corrosion. Aluminum conductors are lighter and less expensive than copper conductors, but they have a higher resistance and are more susceptible to corrosion. When using aluminum conductors, it's important to use special connectors and terminations that are designed for use with aluminum. In addition to the type of conductor, it's also important to consider the size of the conductor. The NEC specifies the minimum size conductors that are permitted for various applications based on the ampacity of the circuit. The ampacity of a conductor is the maximum amount of current that the conductor can carry safely without overheating. It's important to select conductors that are large enough to carry the expected load and to protect the conductors with overcurrent protection devices, such as circuit breakers or fuses. Now let's discuss the importance of proper overcurrent protection. Overcurrent protection devices are designed to protect electrical circuits from overloads and short circuits. Overloads occur when the current in a circuit exceeds the ampacity of the conductors, causing the conductors to overheat. Short circuits occur when there is a low resistance path between two conductors, causing a large amount of current to flow. Overcurrent protection devices, such as circuit breakers and fuses, are designed to trip or blow when an overload or short circuit occurs, interrupting the flow of current and preventing damage to the electrical system. The NEC specifies the types and sizes of overcurrent protection devices that are permitted for various applications. It's important to select overcurrent protection devices that are properly sized for the circuit that they are protecting, and to install them in accordance with the NEC. Improperly sized overcurrent protection devices can be ineffective, allowing overloads and short circuits to damage the electrical system. Furthermore, let's consider the requirements for electrical panels and enclosures. Electrical panels and enclosures are designed to protect electrical equipment from physical damage and environmental conditions. The NEC specifies the types of electrical panels and enclosures that are permitted for various applications, including indoor and outdoor locations. Electrical panels and enclosures must be properly sized to accommodate the equipment that they are housing, and they must be installed in accordance with the NEC. It's important to ensure that electrical panels and enclosures are properly grounded and bonded, and that they are protected from moisture and corrosion. In addition to the technical aspects of electrical calculations and installations, it's also important to consider the safety aspects. Electrical work can be dangerous, and it's important to take precautions to protect yourself from electrical shock and other hazards. Always energize circuits before working on them, and use appropriate personal protective equipment such as gloves, safety glasses, and insulated tools. Never work on electrical equipment when you are wet or standing in water, and always follow the NEC and local electrical codes. By taking these precautions, you can minimize the risk of electrical accidents and injuries. These considerations and applications of the NEC code can lead to a more safer and reliable electrical system.